G'day, Mr. Bennett here. Now, today we're going to be looking at a thing called the photoelectric effect. So what it means is if you shine light onto a surface, onto a metal surface, now metals have delocalized electrons, what can actually happen is you can eject electrons from the surface. Now, there's a thing called a work function of the metal, and that's the minimum amount of energy that you need to supply to eject this electron. So that's actually called W equals H times by F0. Now F0 is called the threshold frequency, and we'll show you what that looks like as well. So this is the minimum energy required to eject an electron from the surface. Now Einstein came up with an equation. The equation is EK max, or the energy of the electron being ejected, is equal to HF. Right, so HF is the energy of the light that's coming through, and then W is the threshold frequency. The difference between the work function, or the threshold frequency there, and the energy that's coming through will determine if the electron will be ejected from the surface, and then also how much energy it will be ejected with. So a very, very simple example here. If we look at this example, so we've got light which has got energy of 6.4 electron volts, and that's been shone onto a metal. Right, the work function of the metal is 3.2 electron volts. Then what will happen is the easiest electron to eject from the surface will be ejected with 3.2 electron volts worth of energy. Alright, so that's its kinetic energy max that will actually have. Alright, so some key ideas here is the threshold frequency F0, that's the lowest frequency of light that's needed to eject an electron from the surface. Right? And in fact, when we do the experiment, you'll find that you'll be doing a graph of kinetic energy max versus frequency, and what that will do is the slope of the line will be in fact Planck's constant, and that's actually how they found it. The threshold frequency is where it hits the x-axis there, and the work function is where it cuts the y-axis down the bottom there. Obviously, if you've got a higher work function, then what we'll do, we'll still have the same slope to the line, but it will actually cut down a bit further there, so it's got a higher threshold frequency. So all of these lines here for different metals will actually be parallel. Alright. Now, when we start looking at the energy of the electrons being ejected, right, there's a minimum frequency. This is some observations that were made when they did the experiment. So there's a minimum frequency where no electrons are emitted. Right, we found that instantaneously the electrons were emitted from the surface. Right, as the intensity of the light actually increased, the energy of the electrons didn't actually increase, but the number of electrons did. Right, so the frequency determines the kinetic energy max of the electrons, and then the electrons are emitted with a range of frequencies. So this is typical sort of spectrum that you see here when we're looking at that. So you've got that line there corresponds to the kinetic energy max there. That's the maximum energy the electrons are going to be ejected with. That's the most common amount, and then that's the minimum energy they're going to be ejected with. Alright, Einstein came up with some assumptions. Some assumptions were light must consist of bundles of energy called photons. In other words, these photons have energy, and what they do is they collide with the electron, they give all of their energy to the electron. Alright? And so that's the nature of light behaving as a particle. Alright? He also saw that the intensity of the radiation is proportional to the number of photons per unit area per time unit. In other words, when you shine the light onto the surface, right, the intensity or the amount of light that you shine on the surface doesn't in fact change the kinetic energy max. All it does is it changes the number of electrons that are going to be ejected from the thing, from the metal. Right? And so we know that the photon gives up all of its energy to the electron instantaneously. Alright, so that's the sort of key thinking there. I'm just going to flick over to what the experiment looks like for this particular thing. So what you have is you have this particular apparatus which is sitting in a vacuum. Right? So what you do is you shine light onto the cathode metal, right? And then you have an anode over here. And so what will happen is as the light shines onto the red line here, it will eject electrons and they'll go across. All right, so that's pretty well what actually happens. So we know that light, the energy the light has, is basically equal to Planck's constant times by the frequency of the light that's used. All right, so then what you do in here is we want to work out what the kinetic energy max is. So if you think of the electrons going across, they'll be ejected and they'll go across and you'll get a current going through the ammeter over here. So what you do is you make it harder for the electrons to get across. So you change the potential difference here and you make it harder for the electrons to go across that gap. And so what you do is you keep making it harder and harder by changing that voltage across here, potential difference. And then what you do is once your current gets down to 0, then you know what the maximum kinetic energy the electron will have that gets across that gap. So that's simply the experiment that we will do in class. So we know that the energy of the photons comes through, that's equal to HF. We know the threshold frequency is F0. The work function is a minimum energy to eject an electron, and that's equal to H times by F0. Just to show you what this might look like in a metal. So in a metal you've got these nuclei, which are positive, and you've got these delocalized electrons. So what we're talking about is the electrons that are closest to the surface that are moving around, and the easiest electrons that you can eject from the surface relate to the work function over here. So let's say the work function is in fact 3.6 electron volts. You've got 6 electron volts worth of, and so you've got a photon coming in with that energy. It hits the electron is instantaneously ejected from the surface with 2.4 electron volts worth of energy. Right? So that's simply how it works. Right? So if we're looking at the apparatus, right? So it comes in here, the electron has 2.4 electron volts. Now if I make that potential difference 2 electron volts, it will get across and there'll be a current shown. Right? If I put 5 electron volts across there, then basically that electron won't have enough energy to get across the gap. So therefore there'll be no current shown. Alright, so anyway, we'll talk about, in our next video, we'll talk about some sort of calculations that you would need to do, and the sort of questions that you might get in a test type scenario. Right, but the key concept of the photoelectric effect is that light is behaving as a particle and not as a wave, as we discovered when we were looking at the Young's double slit experiment and the diffraction gratings. Alright, so very, very important practical that we're looking at here.